Yeah, this is the second lecture in the series on phase-space trajectories. I'll be going into more details on this topic in this lecture. In the last session, we had covered an example of a ball bouncing off the ground. Now, in order to get into further detail in this lesson, I'll be using a new example. Let's take harmonic oscillator as a new example or as our next example. So what's the total energy of a harmonic oscillator? Total energy is kinetic energy p square by 2m plus the potential energy half k x square. What kind of potential do we have here? V is equal to half k x square. We can see that this is obviously a parabolic potential. That means the potential energy curve will be parabolic in nature. That means if you draw the potential energy curve, it will be a parabola. Now just keep that in mind. Now let's analyze the equation of total energy. I'll tell how the phase space trajectory will be mathematically, and later I'll do it in a theoretical manner. Now let's analyze this equation. We'll name it as equation number 1. And now I'm just making a slight adjustment to the equation number 1. So I'll rewrite this equation as p square divided by root 2me whole square plus x square divided by root 2e by k whole square is equal to 1. Now, have you seen an equation like this before? Have you seen somewhere? Well, certainly you have seen. Now this equation, I'll write that equation. These two equations look similar, don't they? Now what is this equation? What is this equation? This is the equation of an ellipse, isn't it? This is the equation of an ellipse. Here we have x and y. Instead of x and y, what we have is a px and x. So what will be the graph between px and x? It will be elliptical, right? Now what I'm telling is that we do not need this to draw the phase space diagram. I have said earlier that our potential is parabolic, so let's keep that in mind and let's draw the potential energy curve first. I hope you understood this concept where we have mathematically we have proved that the phase space trajectory will be elliptical, but we'll approach this in a different method. Now for that, let's draw the potential energy curve. Yeah, I said earlier that the potential energy curve will be parabolic in nature. This is v of x and this is x. This is where the energy is. This is the energy. Yeah, this is the energy. Yeah. Now let's now how do we plot the phase space trajectory from this potential energy curve? How do we plot that? To do that, what we have to do is we'll have to extend this vertical axis downwards and draw a horizontal axis which is parallel to this x-axis. This is x-axis only, and this vertical axis which we have extended is the momentum axis. So I hope this is clear. This is the first step that needs to be followed. So in the next step, we drop a perpendicular from these 2 points. Drop a perpendicular from these 2 points. Yeah. Let these 2 points be x1 and x2. So what's so special about these points x1 and x2? What's so special about them? They are called the turning points x1 and x2 are called the turning points. What is a turning point? Turning points is the point where the potential energy is maximum or the velocity is zero or the kinetic energy is zero. Just imagine the case of a simple pendulum where at extreme positions we have the velocity to be equal to zero. Yeah. Now we'll have to discuss it more clearly. Here we have two regions. A region one or I'll do it in a different manner. There's a shaded region here. This is a shaded region which is inside x1 and x2, and there is a region outside x1 and x2. These two regions. Now, what's so special about the region outside? Now, if you can see, this is the potential energy curve. This is the potential energy curve. So in the region outside x1 and x2, the region outside x1 and x2, we can see that the potential energy is greater than the total energy. Is it possible? So that's my question. Is it possible? The answer is a big no. Why? See in the region outside, the potential energy is above the total energy. The potential energy is above the total energy means what is total energy? Total energy is kinetic energy plus potential energy. So E minus potential energy is kinetic energy. So if the potential energy is greater, the kinetic energy will be negative, right? Is this possible? No, this is not possible since kinetic energy will not be negative. This is not possible. So the region outside x1 and x2, the region outside of x1 and x2 is known as classically forbidden region. So no need to consider the region outside x1 and x2. There won't be any phase space diagram outside that region because the kinetic energy will be negative, which is not possible. So the region outside is classically forbidden. So let's focus on the region inside. Now, to begin with, let us assume that a particle is in x1. That means the particle is in one of the turning points and is moving in this path. I mean towards the left, which means it's moving in the negative x direction. Now I said in my earlier class, if the particle is moving the negative x direction or the negative z direction as I used in the previous class, the momentum will be negative, right? Yeah. I said earlier, now the particle is clearly moving in the negative x direction. Now in the point that I want to make is that at x1 we have the velocity to be zero since it's the turning point. So clearly the momentum will also be zero. Now on the phase space curve, the particle will be here. Now it's moving in the negative x direction, means the momentum will also be negative, and the phase space graph will be like this. Yeah. Now you just go back. The particle has reached here. This is the point where the potential energy is minimum. Potential energy minimum means the momentum will be maximum, right? So it's a negative value, but still the momentum is maximum. Since the potential energy is zero, that's the mean position where the kinetic energy or the velocity is maximum. Now, now it will still continue its motion. Just imagine the case of a simple pendulum. It's still moving in the negative x direction. The momentum still be negative until it reaches here. The velocity becomes zero, and this is the phase space diagram. At this point, its velocity becomes zero, and we can say that here its velocity again becomes zero. That's why the momentum is zero, and this is a turning point here. Now it starts moving. Its motion will be in the positive x direction, which means momentum will be positive and it will be going like this, and it reaches here again. This is the point where the potential energy curve is minimum, and that's the point where the velocity is maximum. So that's why the momentum is maximum, and it will still keep on moving like this. It's now also moving in the positive x direction. The momentum is positive, but the velocity is decreasing. Once it reaches x1, it will become 0. So we have just arrived at what we have proven mathematically before, which is nothing but the phase space trajectory of harmonic oscillator is nothing but an ellipse. Nothing but an ellipse. So this is a different method. I hope you understood this method. Yeah, thank you.